red light. Right. Can you just check, see if we can hear you?
Can you hear me?
Speak loudly.
Oh, I can speak loudly.
Can you hear him?
Can you speak me? Okay, I will use this one.
Yeah.
So, hello, I'm Josselin Clo, and I will speak about part of my PhD about how selfing affects the genetic variance of quantitative traits. Selfing is a widespread mating system, and its interaction with that adaptation process has been studied for a long time and can be divided in two timescales: the short-term advantages, such as reproductive assurance, as you can reproduce without pollinating agents, and the transmission advantage, and you can reproduce with yourself and with other individuals. But despite these advantages, selfing is not the dominant mating system in nature. You only find unilateral transition from outcrossing to selfing, and selfing populations are generally from recent origin. And all these points make that selfing is viewed as an evolutionary dead end, and two long-term disadvantages are proposed to explain this dead end. The first one is that due to lower effective population size, selfing population should accumulate direct use mutation more quickly than outcrossing ones. And the second proposed by Stevens is that selfing population should have less genetic diversity, avoiding adaptation to several environmental change. And I will focus on this point for my talk. So theoretically, the relationship between genetic variance and mating system has been studied for a long time. Under natural conditions, Wright proposed that when a population is shifting from totally outcrossing to a given sampling rate, the equilibrium genetic variance will be 1 plus embryonic coefficient times the original genetic variance in the outcrossing populations. But natural hypothesis is probably not realistic, as most quantitative traits should be under stabilization selection in natural populations. And Lundy proposed that at equilibrium, the genetic variance should not be affected by the selfing in populations, because the higher genetic variance due to homozygosity will be compensated by the per-gene selection of deleterious mutations, and the observed diminution of genetic variance by linkage disequilibrium between mutations having opposite effects on the phenotypes, allowing populations to be close of the phenotypic optima, is compensating by the increased genetic variance due to the diminution of the selection strength, again, this deleterious mutation. But more generally, and more recently, models generally predict a diminution of the genetic variance between obligately outcrossing population and obligately selfing ones, independent from hypothesis, but the pattern for mixed mating populations is still in debate. And this diminution is mainly due to per-gene selection and the linkage disequilibrium due to association between mutations, leading to multilocus genotype populations in predominantly selfing populations in the models. And empirically, these predictions are well supported for neutral diversity at intraspecific scale and interspecific scales. But for quantitative traits, results are scarcer, and a few studies trying to make interspecific confirmation suffer from not much heritability estimates available at the time of the studies. So today I will try to confirm recent theoretical models about additive genetic variance and the effect of selfing, and try to see if more than just reducing additive component of genetic variance, does selfing reduce adaptive potential of populations? To do that, we made a meta-analysis by collecting heritability estimates. We have broad sense heritability estimates, so the ratio of genetic variance over the phenotypic variance, and narrow sense estimate, which is a ratio of additive genetic variance over the phenotypic variance, and we only focus on natural population of angiosperms. And so we collect error estimates for quantitative traits such as flower number, 8 at maturity, and in parallel we try to give to have selfing rate estimates for, in the best case, the population of study, and in the worst case, the species which is studied. And so the total data set is made of 2,800 estimates, and we also made the analysis on the single trait to improve precision of results. And so we focused on 8 at maturity, for which we have 151 estimates. So to answer to the first question, does selfing reduce adaptive genetic variance of quantitative traits in populations? We use a Bayesian meta-analysis using MCMC-GLMM. And so treating selfing rate as a continuous variable and adding random effect study and population within study. And we can taking into account or not a weighting method using the estimation method of the heritability estimates, and so restrict to narrow sense estimate for testing theoretical predictions. And the results are that when you mixed all quantitative traits, you found a significant relationship between the heritability level and the selfing rate, with a mean decrease around 50% between obligately outcrossing population and obligately selfing ones. But the signal is extremely weak, potentially because we are mixing traits with different selection pressure, and so different slopes for each trait we are studying, and because we are mixing population with different properties, such as population size or environmental severity. And you can see that for a given selfing rate, which is most of the time one species, you have a column of estimates. And so we can improve by only using we can improve the signal by only using one trait. And when we use the trait at maturity, we also found a significant relationship between the heritability level and the selfing rate, with a harder decrease of heritability value between obligately outcrossing and obligately selfing population, and with a very much impact of selfing on the heritability level. And we can also show that the pattern for mixed mating population seems to be a decrease, a really continuous decrease of the genetic variance in function of the selfing rates. And so in the second time, we can ask if additive genetic variance is a best proxy of adaptive potential for selfing populations. Generally, to predict change of phenotypic traits, you can use the breeder equation or the Robertson-Pride equation, which made hypothesis of random mating and using additive component of the genetic variance to predict the evolution. So for outcrossing population, you are in an equation with hypothesis of these models, and so narrow sense estimates of heritability could be good proxy of adaptive potential. But for selfing population, you broke the hypothesis of random mating, and due to lower effective recognition rates, you can maintain genetic association between loci having a positive effect for fitness population. And so, according with the literature, broad sense estimate could be a better proxy of adaptive potential for selfing population, because it contains this interaction variance, which become heritable. And so when comparing the narrow sense estimate for outcrossing population and broad sense estimate for selfing population, we also found a decrease in the mean heritability level between these two mating systems, showing that more than just reducing adaptive genetic variance of quantitative traits, selfing should also reduce the adaptive potential of population, but with a smaller degree than for additive components. And so, in conclusion, we have seen that we can confirm theoretical models and showing a negative relationship between additive genetic variance and the selfing, with a decrease of around 50 and 90%. But we also show that the pattern is general but not universal. We have a great variability between populations, and so other mechanisms other than the mating system should explain difference in observed genetic variance in populations. And when considering other components than just additive genetic components for adaptive potential of population, we have shown that selfing also decreases the adaptive potential, but by a smaller degree than for additive genetic variation, showing that we have to be careful when we question about what is the adaptive potential of population and how the mating system could interact with that. And all of the results give support to the stable state hypothesis. And to go further and to study this effect of selfing on genetic architecture, we use a simulation model from Diala Bouawad and Denis Rose by extending the model. So in a model with purely additive loci at mutation selection drift equilibrium, you can decompose the additive genetic variance in several terms within loci terms with the genic variance and the homozygosity effect, and between loci components which tend to be negative for predominantly selfing populations because you create linkage disequilibrium between mutation having opposing effect on the phenotypes. So you create linkage disequilibrium between mutation having negative and positive effects, which tend to create a negative component here. And we are thinking with my PhD supervisor that residual allogamy could release these negative components and allowing selfing population to answer to an environmental change. So that's all from me. Thank you for attention and thank you for committee organization.
Thank you very much. There's time for a couple of questions, I think.
Hi there. Building on some of the comments from the previous talk, is there any evidence that selfing angiosperms have greater phenotypic plasticity or ability to withstand stress and so on and so forth through phenotypic plasticity processes?
Sorry, I don't understand the question. Can you repeat, please?
Yeah, so is there evidence for greater phenotypic plasticity in selfing species, for example? So is there sort of adaptive responses, not necessarily genetic, but they have greater phenotypic plasticity to deal with environmental changes, things like that?
I don't have in mind empirical results for greater phenotypic plasticity in selfing populations compared to what Cosim wants, but
just checking, in your meta-analysis of the estimates of heritability from plants, these are wild plants, but usually grown in a controlled environment?
yeah, most of the estimates are made in greenhouse experiments.
Are there any estimates from populations in the wild?
Some, but the majority of estimates are people that took seeds in the nature and then made growing up in greenhouse experiments.
Okay, thank you.
Well, I think we probably stop now and plenty of opportunity